Another thing that seems related, and it is in a way, but it's not identical, is an area called sequence-to-sequence learning. So this is when you're trying to convert a sequence of data, like a time series or text, into another form. So transforming it to a different format. The canonical idea is to basically do natural language translation, right? To turn English sentences into French sentences, or translate Chinese to English or German or whatever. Or translate one programming language to another. It should be easier in a way. So the idea is you have a sequence of data, and now you want to produce a new sequence that is somehow equivalent or related to it. And so using some of the same idea, that you've got your inputs and your outputs, they're known, and you want to have an encoding in the middle, but and you can even do it where the input is used as the output. So you basically train it initially to say, well, can you even just regenerate English sentences from English sentences? Learn a model that does that, and then I'll teach you French, because maybe that will be useful in some way, in the same way that a CNN, right, a convolutional neural network with multiple hierarchies of features might learn essentials about images, like line edge detectors and gradients. In language, you might learn something useful just by regenerating your own language first, and then forcing it to basically start from that point and learn how to translate to a different language. And this does often work quite well, because you're getting a lot of the basics of the concepts of your own language as a separate training task from the other one. But an essential part of this as well, obviously, is that it's over time, right? So the different data points arrive in sequence, right? And so it's different than an autoencoder that we're talking about, where you've got each X, that's your input, is a data point with features, right? So we're talking about the actual features that, of a single data point. In sequence-to-sequence learning, you've got a series of X data points in time that have their own features as well, and you're trying to reconstruct that. So in addition to saying you're doing this kind of approach, learning and encoding, the thing that's in the front is more of a recurrent neural network. So an LSTM is often used for this. So you're learning LSTMs on the inputs, then some encodings in between them, and some LSTMs on the outputs. This is getting more complicated. You can go and read more about it. I will connect it to this other thing from text processing just at the end of it, because it is a very ongoing field where a lot's being learned about what is actually required and what actually isn't. And so the latest way of doing this actually is to ditch the LSTM entirely and just use something called attention, and do it over the data. So that makes it different again. But so just to give you a kind of distinguishing about autoencoders not being exactly the same as this. So in a denoising autoencoder, we modify this task of taking the data and just reconstructing it exactly to taking the data and a corrupted version of it and trying to reconstruct the uncorrupted original version. Now this is becoming a little less unsupervised, so it's self-supervised because we're not getting any new data. We're using the input data we were given, but we're basically modifying it by applying some noise or some other distribution to it, sampling an actual input data, the noisy one, that we'll use in the model, and then trying to reconstruct the original uncorrupted data as the output of the network. So while we're training it, we have access to the original uncorrupted data and the corrupted data. And what we're trying to learn then, right, is a reconstruction function that can clean up this noise and give us clean data. And so if we think that our input data in the real world is going to have these kinds of noise patterns in it, then this model would be trained to do that, to clean that up, which is nice. This wasn't the entire reason just to do it. They were also trying to make sure they build a model that is a little bit more robust and generalizable because it's not just trying to produce the perfect data set, it's trying to handle data points that might be similar or in the neighborhood of that via some corrupting distribution. So this kind of improves the performance of the autoencoders a fair bit, and it actually is related to a lot of things that are happening more recently as they were picked up again. So what we're actually learning in this case, you could think of the red points here, the red X's are the original clean data points, and we have some kind of noise distribution that we're adding to it. And every time we hit this data point, training input data point, we might have a different sample from that noise distribution, so we won't always get the same X tilde. Which is good. So we're learning something a little bit more robust. So we're essentially learning a kind of a gradient that tells us how to get back to the real manifold of where the data is, right? So it's more explicitly trying to learn the manifold, as we've kind of talked about. In a sense, if you're at some data points X tilde, how do you get back to the real data, right? So for every point in space, it kind of learns vectors that point towards the places where the real data would be. What's the closest way to get there? So it's a nice way to kind of encourage this to have a bit more flow, so that at every point there's not just the reconstruction of the exact data point, but at least it's going in the right direction, because it will have sampled many different data points in here that are error versions of maybe a range of points around the space. Obviously, this is just a two-dimensional representation of something that could be high-dimensional. But when you're trying to optimize for this noise, it gives you more data points for every point in the real full feature space to tell you how to get there, right? If we're only training on the actual data points, we can have a network that does well and reconstructs it by just giving it points on this curve. But then if it does get data points later on outside that curve, it isn't likely to know what to do very well, right? Whereas when you train it this way with a bit of noise added, it at least has some experience seeing data points outside that are nearby and tries to get them in. Obviously, if the noise in the real data set, the real world at test time is very different than the noise used at training time, it may not be that useful, maybe to go in the wrong direction entirely. But if you understand something about the noise of your system, that can help. And it seems to work quite well even if you don't know the noise of your system that explicitly, because there's only so many ways that it can be noise. So adding more layers, so making it more deep. This can obviously help, like deep learning. We've shown the places that more deep layers can give you improved power for classification and all kinds of problems. It also can help you get by with less data because you're learning more kind of independent ways of representing that data and converting it. But it doesn't necessarily always help. Some people have had success just combining lots of shallow autoencoders and using the idea of ensembles, just like we talked about with random forests, where you have many different simple models and combine them together, say boosting or something like that. You could have very simple autoencoders with just one hidden layer or three hidden layers where the middle one is quite narrow, and then have them be trained separately. They have independent tries and combine those together and use like voting to pick the best one. That has sometimes shown to be just as well. So there's no clear idea that making them much deeper helps a lot because you have a trade-off of how long it takes to train it in terms of updating. So backpropagation will take longer with more hidden layers, but you could maybe learn a richer model with less data. But it's one of those things that's trial and error. Autoencoders can be used for a lot of things. They're a good go-to if you need to reduce the size of your data or learn some representation that you want to connect to a different problem. So we've talked about taking inputs from one data set, like images, and then using kind of learning from multiple sources, right? So we talked about this a little sometime recently. So say you've got some data set that comes in as images, right? And so you've got your your series of images, and then you've got some other input that's text. Well, let's not have text. Let's have just numerical input if we don't have time, right? Right, so we got a bunch of features. And so you could learn some autoencoder, right, that basically does this, and it's training X to X and doing that. And you could do the same thing with your image data, right? So we could have CNN layers, right? Max pooling layers, and then you repeat 3 times, some more, and then you have some fully connected. But you could do it as an autoencoder, right? Where it has a small number, and then as the output, you do the same thing. And so you have to have reverse CNN and then produce the image. So people have done that as well. I'm going off on a tangent here. What I'm talking about is if you wanted to combine these together, right? So what if you wanted to say, now I've got my image data, you've got some problem where you have your image data and your numerical data, but you want to have them both go into some black box and have your output classifier, because you want to be able to use the text and the numbers. A way to try and do that then is to extract the encodings, right, that you learn in a kind of an autoencoder approach and combine them together, right? So instead of just using the image directly, you pump the image into the first half of this network and then take the output here, right? And so in our numeric data, we send it to this network, and then we take the output of those encodings, and those encodings just can get concatenated together, right? And so after that, then we have the black box just being, right, encoding 1, encoding number 1, encoding number 2, and have them concatenate together. And have some fully connected network, right? And you could have however many layers of that you're going to have until you get your classification as the output. So that's kind of a general pattern you can do with a lot of things, and it's a good way to do multi-sensor fusion, like different types of data, different data formats, where you learn a network for some other purpose, like classification, or for as an autoencoder itself. If you don't even have a label at all, you can always go back to learn an autoencoder of this data and then take the embedding, the encoding, I guess we'd call them either way, and use those as the way to turn them into some common language, right? Because once we get here, these are all just vectors of numbers, right? And you got a bunch of vectors and inputs, and then you have a fully connected network that finds the patterns in it. You could use PCA to get these encodings instead, and just use the eigenvectors, but a neural network is going to be more general, right? So that's just another thought of how they can be used and often get used. A very specific one that connects to us, or what we've talked about with text, is this model of BERT and transformers, this model of transformers, which has its own complexities, so we're not going to go into it a lot of details, but I think you guys have the next step needed to kind of go and look at that after this course. And in that case, they're talking about language, so they're talking about a sequence of words. So just like we did with Word2Vec, you have a sequence of words, you turn them into some kind of bag of words counting or one-hot encoding to represent the words themselves. And then instead of, like we talked about, that Word2Vec almost feels like an autoencoder because you're learning mappings, right? A representation of words and what the next word is going to be, right? But in an autoencoder, the model itself is, if at all, a very simple neural network, because it's really just literally mapping individual words to the next words that will come, or to the word that would follow in the middle of a gap, depending on what way you're doing it. But a more general way would be to say we're actually going to learn autoencoder, a neural network that's going to have multiple layers, can learn all these relationships between words across the text, and try to do that. So BERT is a way that does this using a couple other advances that people have come up with, and it's definitely a self-supervised approach, and this is what was inspiring Jan LeCun's discussion that I started the lecture with. They use a denoising autoencoder, just like we've talked about, where they feed in the words in sequence, and then some percentages of the words, in the original paper is 15%, they mask out the words and just knock them out of the text and say, okay, now predict what that word would be, because I'm just randomly knocking out 15% of the words and try to fill in the words. And so we're forcing it to learn a representation of the text you're giving it, but by hiding some of the words, right? So, I mean, Word2Vec did that, literally looking for every word and treating it as the next one coming. In this approach, they're looking over a large text corpus and knocking out words randomly, but then they use a denoising autoencoder in the middle, right? So they see the original text and the knocked out text, and they try to learn the model that lets them figure out what the missing words would be. But a denoising autoencoder would try to predict the entire text. In the case of what they're doing with BERT, they only try to predict the missing words, right? So it's a simpler task because you don't have to reconstruct everything. You only want to fill in the gaps, right? So it'd be like for the denoising case where we add noise to some of the data points and we only want to fix those data points, but we don't try to predict the unnoised points. So basically, as a figure is from that article that I was talking about on Facebook that kind of overlays some of the recent things here, so you can read through that in more detail. They take a large number of text articles and run them through a model that's trying to predict what words would come to fill in the gaps that have been added, and then they have a corrupted version of that text. They're basically trying to predict the words that were masked, right, that were knocked out. The other kind of important aspect with that one is that they basically stepped aside from using recurrent neural networks anymore, just because it's a text corpus and words can be seen as arriving in time. They basically get rid of using a recurrent neural network, so you don't have to have that complexity of time, and they use a different approach called attention that kind of focuses in on the words that seem most relevant for the training, which is related to what we talked about with investigating individual neurons in the CNNs when we're looking at the cat picture from YouTube, kind of taking the same idea of like pick individual neurons and try to figure out which features were most important for training that, and then focus in on learning those. And so it doesn't need to remember how things are related over time explicitly. So it's been very successful for text and natural language understanding, and partially because it's easy to represent the distribution of words, right? We have this way of representing individual words and how many are in a document. If you have a lot of documents, those representations seem to be quite representative of the actual data and the relationships between them, which is evident from the fact that Word2Vec, which is a very simple method, actually extracts a fair bit of meaning directly. As they were talking about in that article, just to wrap up what he was talking about, he sees this as the greatest challenge in AI right now, is to figure out how to do this for other domains, right, images and videos, because it's not as easy to come up with a distribution over high-dimensional spaces with lots of colors and pixels and everything. So these models don't show as much benefit yet for those domains, but people are trying to make that work. So there's lots of things to look at in that direction, but it's a very hot area. Basically trying to take some of these ideas coming out of autoencoders and connect them to really complex data. So that's just a taste of that. I think it's a central concept of the autoencoder. and how that can be used and how it fits into deep learning in general, and how not to trust whether someone is demanding a thing being unsupervised or supervised, but that there's quite a spectrum in between them. So you need to think about what data you have, what labels you have, what your supervisory signal is. I'm trying to start thinking of it more that way. And where it's coming from, and when you're deciding what algorithm to choose or whether you think it's reasonable that it will work, right? Is there enough signal coming in for you to learn a model? Does your model, its representation, have enough capacity to learn what you're trying to learn? These are things that aren't explicitly like known, but there's some guidelines, right, on which methods will work better given the task you have and the complexity of your model, and the source of the signal that you're trying to train against. Okay, so I'll end it there. And yeah, so then there's like I said, there's another lecture on variational autoencoders you can look up to get a little bit more depth on that particular method. Great, thank you.